Multiplying. Go slow. Go slow when you are multiplying. All right? Listen. No, seriously. None of the math that we are going to do today is difficult. You are going to be adding and you are going to be multiplying. That's it. The process of figuring out which numbers to do it with takes time. It is a pattern. Go slow. Okay? And I want you to remember this phrase. You ready? Row by column multiplication.
Row by column.
Forget it. Don't lie. Row by column multiplication. Matrix operations, addition, subtraction, scalars, multiplication. They all take practice. Okay? Addition, subtraction, scalars are pretty simple compared to multiplication. But it all takes practice, and over the next few days, you are going to get a lot of practice. Okay? But you will be proficient by the end of the week. None of it is difficult math. It just takes a while. Okay? Alright. So row by column multiplication. What we're going to do is we're going to take every row of the first matrix. Okay? Every row of the first matrix. And we are going to multiply by every column of the second matrix. And then what we're going to do is we're going to multiply the corresponding elements. So the first element of the first row gets multiplied by the first element of the first column. And then the second element by the second element, and the third element by the third element, and the fourth element by the fourth element, depending on how many rows and columns we have. Okay? So this kind of gives this formal breakdown. All right? I'm just going to dive right in because I think it's better if we see some actual numbers. Okay? But remember, every row of the first will be multiplied by every column of the second. Every row of the first will be multiplied by every column of the second. So we row by column multiplication. All right? Let's do this. Row, every row of the first by every column of the second. So we're going to start with the first and the first. Multiplying 1 times 0 and 2 times 3. Row of the first times the row of the column of the second. So we're going to multiply the first element by the first element and the second element by the second element, and then we add those together. Okay? We're going to multiply the first element by the first element, the second element by the second element, and then we add those together. Okay? With multiplication. Tomorrow or the next day, I'm not sure which, whenever I have time, I'm going to show you how you can use your fancy-dancy TI-84 calculator to check your work. Okay? It's a little bit of a time-consuming process, but if you have time left on a quiz and you want to check, it allows you to check and then pinpoint where one or more elements may be off and not have to go through the entire process. With that being said, Michael, you good? I don't think you're dozing off there. You don't pick your head up. Work is required or you get no points, okay? Work is required. You get no points. Got it? Okay. So, here's what the work is going to look like. We said we're going to multiply the first by the first, right? So that's 1 times 0. And then the second by the second, that's 2 times 3. And then we're going to add them together. That's the work that I want to see. And then if you want to add those and then, or if you want to multiply them, then add them and show us 2 separate steps to get your answer, that's fine. But I need to see this step. That is not negotiable. Hurry up. Okay, first row, second column. Same pattern. Okay, because every row by every column. So the first row is going to be multiplied by every single column in the second matrix. The more columns we have, the more multiplication we do. The more rows we have, the more multiplication we do. Okay? First row, first column, first row, second column. So 1 times 2 and 2 times 4. So the first row gets multiplied by the first column, and that gives us the first element of our product. The first row by the second column gives us the second element of our product. And we would continue that pattern through all the columns. When we run out of columns, then we go to the next row. Continue that process through all the columns until we run out of columns, and then we would go to the next row until we run out of rows.
So
Okay.
the next ones would be 1 times 3, 2 times 4.
4, 0, 5, 3. So we're done with the first row. So now we go to the second row. You were watching. Okay. Second row, first column. 4 times 0, 5 times 3. 4 times 0, 5 times 3. And then second row, second column. 4 times 2, 5 times 4. That is the work that is mandatory, non-negotiable. I need to see that. Okay? Need to see it. Now we just simplify it all up. So if I have 1 times 0, which is 0, and then 2 times 3,
6.
so 0 plus 6 is 6.
I'm sorry.
Okay? 1 times 2,
2.
2 times 4, add them together. 4 times 0, 5 times 3, add them together. 4 times 2, 5 times 4, and then add them together. I see you. There's our product. Now when we added and subtracted matrices, they had to be the same order. Okay? The same number of rows and the same number of columns. That's what we did here as well. We have the same number of rows and the same number of columns. But multiplication doesn't have that same limitation. The limitation with multiplication is that the number of columns in the first matrix has to match the number of rows in the second. Okay? That'll tell us whether or not we can actually multiply it. The number of columns in the first has to match the number of rows in the second. And we're going to get to an example later where we can't multiply. And as long as you're kind of aware of this process, it'll be easier because you'll realize, oh, I literally can't do it. Okay, I don't have enough numbers to multiply. Okay, so this gives us our limitations for whether we can or cannot multiply. So, a couple things. One, we look at the columns of the first and the rows of the second. That tells us, can we multiply them? If they're the same, then yes, we can multiply them. And then, the rows of the first, followed by the column of the second, tells us what the order of our product will be. Now it tells us how big our matrix is going to be. So we're not going to end up, most of the time, unless we have square matrices being multiplied, we're not going to end up with the same order in our product as our factors. So let's look at A and B here. Matrix A is a 1 by 3, 1 row, 3 columns. Matrix B is a 3 by 1, 3 rows, 1 column. The columns of the first has to match the rows of the second in order to multiply. Okay? Because I have to have, if I have 3 numbers here, I have to have 3 numbers here to multiply when I do the row by column multiplication. If those don't match up, then I have numbers missing and I can't finish the multiplication. Okay? And then the size or the order of my product is going to be determined by these outside here, the rows by the columns. And since I have 1 row and 1 column, I'm only going to end up with a 1 by 1. Just 1 element. That's it. 1 element. So my product is going to be 1 element. All right? So I need to take the first row, and multiply it by the first column. So what's the first element of the first row? -2 times -4. -2 times -4. And I'm still going in the same column. So now I do the second element times the second element. 1 times 1. And I'm still in the same column. So I do the third element by the third element. 2. Okay? So we only go to a new element when I have a new column. Since my second matrix only has 1 column, then I can't go to a new column in my solution. And I only have 1 row, so I can't go to a new row. So I'm going to have 1 row, 1 column. So 8 plus 1 plus 6 gives me what? So my answer is 15. So 1 by 1 matrix for 15. That was A times B. Now, I'm going to take the same 2 matrices, and I'm going to multiply them in a different order. And I'm going to get a different answer. Not complicating it. I'm just showing you. Same matrices, but instead of doing A times B, now we're going to do B times A. Now, there's a couple typos here, so let's fix these. This is B, this is A, and this is going to be BA. Switch those. All right? So, again, matrix B is a 3 by 1. Matrix A is a 1 by 3. Since the number of columns in the first matches the rows in the second, then I can multiply these together. But because I switched the order, now I'm doing a 3 by 3. Same matrices, different order, vastly different product. Okay? So, first row by first column. So what am I multiplying? 4 times -2. Do I have anything else in this column for -4 to be multiplied by? In this column? No. So now I move to the next column. So now I'll do -4 times 1. All right? Do I have anything else in that column to multiply -4 by? No. So now I move to the next column. Notice how I'm not adding. Because there's only 1 element in each of those columns for the multiplication. I'm not adding those. I'm moving from column to column. Okay? -4 times 3. Not when I go from column to column. You only add them. See, if we look back, see how I was in this column?
Yeah.
All of those, I will add the product of this and this. I only have 1 number in this column, so it's this times this. There's no other element. So then I move to the next column, and then the next column. And now, there's no other columns, so now I go to the next row and repeat the process. -1 times -2, and then 1 times 1, and then 1 times 3. And then I go to the next row. What's the next row going to be? Yep. 2 times 1, and 2 times 3. So again, that's the work that I need to see. And then we can clean that all up. So go ahead and multiply. What's the first row of my product going to be? 8. Keep going. 4. There you go. -12. Keep going. -2. 3. 3 by 3. I multiplied the same things, but in a different order, and I got a different product. It's not confusing, it's just different. But remember, because we're doing row by column computation, if we change the number of elements in the row and the number of elements in the column, now we're changing our computation because it's row by column. So in this one, I had 3 elements in a row and I had 3 elements in a column. Here, okay, I had 1 element in each row and 1 element in each column. So that's what's changing why the orders are different. Yeah. 1 row with 3 elements, 1 column with 3 elements, versus 3 rows with 1 element, 3 columns with 1 element. And that's what's changing the order. Row by column. So we can see matrix multiplication is not commutative. A times B is not going to equal B times A. Okay? It's not. Alright? A times B is not going to equal B times A. So, I've got a 2 by 2, and I've got a 2 by 4. The columns in the first matches the rows in the second, so our multiplication is good. The rows of the first and the column of the second is going to give us our order. So 2 by 4. Alright? I'm going to have to write this small. Let's see if I can do this. Alright? So what elements are in my first row? 2 and 3. So I'm going to multiply 2 and 3 by what? 0 and 2.
Oh, 0 and 2.
Rows go side to side, columns go up and down. So 2 times 0 plus 3 times 2. See, I'm adding because I have 2 elements in the column. For every element in the column, we add it. Okay? 2 elements in the column, and add them together. Also, 2 elements in the row. So 2 elements in the row, 2 elements in the column. I'm adding 2 products together. Okay? Now what?
4 times 0.
I'm still in this first row.
Oh.
Yes.
2
Because
times,
there's 2 elements here and 2 elements here. I need to
2
add
times
those.
1, 3 times negative.
Good. So now we're going to the next column. Next column is 2 times 1 and 3 times negative 1. And then we're going to add those. First row, second column. And 3 times 1, negative 1. Next one.
2 times 3 times 2.
Yep. 2 plus 3, 3. I have to write a little smaller so I don't have room.
2, 3 plus.
Yes, you will have plenty of space. And then 2, 3 plus 3 times. Okay, so that's my 4 elements of my first row of my product. Now I'm out of columns, so now I have to do what?
Go to the other row. Go to the
Go down a row. So 4 and 1.
4 times 0. 1 times 2.
Now, watch this. Look real close. Look at this first row. 2 times something plus 3 times something. 2 times something plus 3 times something. 2 times something plus 3 times something. So, I can start out and I go, okay, well, everything in this is going to be multiplied by 4 and 1. So I'm going to have 4 times something plus 1 times something. 4 times something plus 1 times something. 4 times something plus 1 times something. Over and over and over. Now, watch this. Even better. You ready? Don't blink. 0, 0, 2, 2. 1, 1. Negative 1. 2, 2. 3, 3. 3, 3. 4, 4. Look at the number above it. That second number will always be the same as the one above it. 0, 0. 2, 2. 1, 1. Negative 1, 1. Or negative 1. 2, 2. 3, 3. 3, 3. 4, 4. Those always end up being the same. pattern. Every row is being multiplied by every column. There's only so many numbers we can use. So you can go through it and you can look at it step by step and say, okay, 4, 1, 0, 2, 4, 1, negative 1, negative 1, 4, 1, 2, 3, 4, 1, 3, 4, and then double check to make sure that pattern lines up. And then we can simplify from there. Okay? So I've got 2 times 0 plus 3 times 2 is what? 6. 2 times 1 plus 3 times negative 1. I'm at the second element now here. So 2 times 1 plus 3 times negative 1. 2 times 2 plus 3 times 3. 15? 13. 2 times 3 plus 3 times 4. 4 times 0 plus 1 times 2. 4 times 1 plus 1 times negative 1. 4 times 2 plus 1 times 3. 4 times 3 plus 3 times 4. 16. I think my 3 disappeared over here. It's not hard work, it's a lot of work.
On this, it's the 4 times 0, right?
Yep. Yeah, so once we do the second row, 4 times 0, 1 times 2, 4 times 1.
So it's 2 times 0, 3 times 2.
Yes, 2 times 0, 3 times 2. All right, now, again, switching the order is going to change the product. Now, in this case, the number of columns does not match the number of rows, which means it's not possible. And I'm going to show you why. Because if you forget to check, you should be able to figure out pretty quickly, oh, this is something I can't do. Row times column, okay? The row times the column. So what's the first two things I'm going to multiply? 0 and 2. 0 times 2 plus, what's the second two things? Third thing.
2 times.
So first element, second element, third element. There's not enough numbers in that column to match with the numbers in the row. So I don't have enough to do multiplication. Does that make sense? That's why the number of columns has to match the number of rows so that there's enough numbers here for here. So if you forget to check, you should find out pretty quickly that you can't do it. Just like if I try to add two matrices, if I try to add a 2 by 2 to a 3 by 3, I can't do it. So that would be an undefined sum. This is an undefined product. Get that, and you can say it's undefined because the number of columns in the first does not match the number of rows in the second. All right, some properties. Yesterday I mentioned that matrices have a lot of applications. Computer screens are lit up by using a matrix. So the matrix tells each pixel what color to be. And then they change the numbers in the matrix. It changes the colors that correspond with it. And then, boom, we have a computer screen that's all lit up with pretty pictures of your favorite movie or game or whatever social media. All right? So if I have this grid of gray squares, and I have numbers that the computer associates with each square, 0, 1, 2, and 3, for white, light gray, dark gray, and black, I can represent this in a numerical matrix. Okay? So, if my first panel is dark gray, what number would correspond with the first element? 2. What about the second panel? Third panel? Fourth panel? Okay? So I can represent the whole thing in a numerical matrix that corresponds with those colors. Now, let's say I wanted to take the entire matrix and I wanted to make the screen one shade darker. What would I do with each of those elements? Multiply it to make it one shade darker. Add what? Add 1. Add 1 to each element. And now the whole screen will be one shade darker. One shade lighter. If I wanted to make it 2 shades lighter, subtract by 2. 2 shades lighter would be subtracted by 2. Okay? So we could adjust it. We could adjust it accordingly, and as the picture changes, the numbers would change to match the picture. Yes, because matrices make everything easier. Oh, they do. They do. I promise. Okay? Oh, collective groan. No, I'm not complicating it. I'm making it easier.
The time I saw that graph, I was like, no.
Oh my God.
First, we're going to write the triangle's vertices as a 2 by 3 matrix. The rows, the 2, representing the x and the y, the 2 parts of the ordered pair. The columns representing each of the points, because I have 3 columns, 3 points. Okay? So, we're going to start by writing the vertices as a 2 by 3 matrix. And I'm just going to pick these as the first point, second point, and third point. And note, your matrix, your rows will be your x's and your y's, and then your columns will be your first point, your second point, and your third point. What's the x of my first point? -1. What's the y of my first point?
3.
What's the x of my second point?
2.
What's the y of my second point?
4.
What's the x of my third point?
4.
What's the y of my third point? So that matrix represents those ordered pairs. So now what we want to do is we want to take that entire triangle and we want to shift it 3 units to the left. What values does that change if I'm moving it to the left?
X
An
values.
x. So what am I going to do?
Add the x values by 3.
I want to move to the left.
I was subtracted by 3.
Subtract by 3. If I want to take all of my x values, if I want to take all those points and I want to move them left 3 units, I'm going to take each of those x values and subtract 3. Now, I also want to move it 1 unit down. What is that going to change?
Subtract the y
By 1. 3 minus 1, 4 minus 1, -1 minus 1. And then when I simplify that, that's going to give me my new ordered pairs. What's -1 minus 3? What's 2 minus 3? What's 1 minus 3? 3 minus 1. 4 minus 1. -1 minus 1. -2. There's my new matrix. So my ordered pairs, I can pop this back into ordered pairs, x over y. -4, comma 2. -1, comma 3. -2, comma 2. Those, about here, and -1, 3 is here, and -2, -2, -2 is here. There's my new triangle, shifted left and down. And down. Perfect. Okay? Yeah. Can you wait like 3 minutes for me to finish? I'll let you leave. Now, I want to shrink the perimeter by half. If I want to shrink the perimeter by half, what can I multiply everything by?
1/2.
Shrinking and expanding is just multiplying by a scalar. So if I wanted to double the perimeter, what would I multiply by? 2. If I wanted to triple the perimeter, what would I multiply by? 3. If I wanted it 5 times larger, 5. If I wanted half the size, if I wanted a quarter of the size, 1/4. So if I want to expand it or shrink it, I'm multiplying by a scalar. And so since I want it to be half the size, I multiply by 1/2. What's 1/2 of -1? -1/2. Half of 2. Half of 1. Half of 3. Half of 4. Half of -1. And those, again, give me new ordered pairs. -1/2, 3/2, which would be -1/2, 3/2. And then 1, 2, which gives me this. And 1/2, -1/2, which gives me this. And now my perimeter is half the size. Matrices make everything easier. But if I wanted you to do both of those together, if I wanted you to shift it and shrink it, or shift it and expand it, then we use the matrices and we can do that all in one go. If I wanted to take this one that I shifted and also shrink it by 1/2, I would take this final matrices, multiply it by a scalar of 1/2, and that would take this triangle and then shrink it and let me know exactly where all those points are. Matrices make everything easy.